And okay, that's on. Okay, welcome everyone. Thank you for joining for our OpenMP webinar. It's the number 4th, I think, in the series, the number 4th. So we have Christian Terboven and Michael Klemm today to make the call as usual. So thank you very much, Christian and Michael, for giving this webinar. And now I give the floor to Christian and Michael.
All right, thank you. So today we're going to talk about GPU offloading, and following our tradition that we had for the past webinars, we're going to start with Q&A about anything that you are interested in to ask about the last webinars or in general about OpenMP. So please unmute and ask if you have a question. No questions? Don't be shy. All right, if there are no questions, that's cool. All right, so what we're gonna do is I'm gonna lead into the introduction to GPUs. As usual, if you have questions on the fly, please feel free to type them into the chat window. While I'm speaking, Christian will answer those questions. And when he takes over the speakership, I'll be answering those questions. And if we see that the question is important enough, we will also kind of interrupt the talk and start answering that question as we go. All right, so I'm going to introduce OpenMP offload features. And for that, Christian and I pretty much have a running example. And we chose kind of an hello world problem of HPC, and that's saxpy. So, you know, the operation of scaling one vector element-wise and then adding another vector on top of that. And here's the code on the slide. The blue part, that's the part that we are particularly interested in. So this is the code we want to execute on a target device. So in this case, a GPU. The green code before and after that offloaded code, that is just, you know, timing code so that we can do some low man's measurements. And of course, it's also just, you know, to have a little more meat on my slides and a little bit of more code to show so that you have a more visual experience. The disclaimer I have to make, though, is that, as I said, this is more like a hello world example. So don't do this at home, right? Typically, BLAS libraries have a highly optimized version for your processor, but also for your favorite GPU. And so, you know, instead of rolling your own saxpy operation, you should probably just call into your favorite BLAS library for your favorite architecture and use that instead. That's a lot easier, less error prone, and more productive. All right, but nevertheless, it's a good example to show how you can do GPU offloading with OpenMP. All right, let me start with the device model. So as of version 4.0, the OpenMP API specification supports accelerators and coprocessor. It's not specific to GPUs, and you'll see from what I will explain in a minute that it's way more generic than just standard massively parallel GPUs. So the device model technically is one host that contains processors that can execute the standard OpenMP threading that we have in OpenMP since 1997. And then there may be multiple accelerators, coprocessors, or offload devices of the same kind for offloading. So these are devices that are somehow attached to the host. The host has a mechanism indicated by this blue line here to talk to the accelerator, to send data to those accelerators, then give a command to execute a certain piece of code, and then get data back from the accelerator. And anything that is that adheres to that model will be can in theory match the OpenMP device model and can be used as an OpenMP offload device if you have an OpenMP implementation for it. As a funny anecdote, when Christian and I went around the country to show OpenMP 4 features, we actually used in one talk, we used the audience as an offload device and pretty much gave them little stickers with numbers on it, let them compute, and then collected it, and just to show that the device model of OpenMP is rather generic and very, very flexible. We do support the same kind of coprocessor in a system. So that means, whatever the implementation exposes as kind of the same device, right? So for instance, for AMD systems, you could have a bunch of Radeon Instinct cards in your systems. And if you, you cannot mix and match them with, say, NVIDIA GPUs, right? Because the implementation doesn't support that. What in theory would be possible, though, is if you have 2 generations of different Radeon Instinct cards, the implementation could treat them as the same kind of architecture and expose them as a single lineup of GPUs. All right. Okay, so key takeaway: host for regular multi-threading, and then the accelerators are devices that are just attached in a certain way to the host so that they are programmable from OpenMP. All right, now the execution model. So the way we designed OpenMP offloading is that the offload region, so the code that you want to execute on your target device, is lexically bound to the scope of the construct. So there's a begin statement in C, C++, that's a curly brace, an opening curly brace, and a closing curly brace to end the statement. In Fortran, there's a begin directive and an end directive, like I'm showing on this slide. And when the statement begins, so the offload directive begins, we create the data environment. So that means the buffers and the storage on the GPU or the accelerator is allocated. The data transfers happen if needed. And then at the end of the construct, the data environment is automatically destroyed. And the buffers are cleaned up and released on the target device. Data transfers, if we need them, are done at those curly braces or begin end statements too. So if we need to upload data from the host memory to the device memory, that happens at the opening curly brace or the begin of the construct. And the download of data from the device memory to the host memory happens at the closing curly brace or at the corresponding end directive of the construct. And I put in if needed, because we can also support something like unified shared memory, where we don't need to actually copy data around, but rather then the data transfer is more indicating transfer of control, so that the implementation knows that now the GPU has access to that particular piece of data. All right, let me show you what you can do. So here I'm showing a target construct with that will execute just some arbitrary code. The first thing that we can do is we can do an allocation. That means we can create an empty buffer, an uninitialized buffer of a certain size in the device memory of the GPU or the coprocessor. Then we can transfer data from the host memory into that buffer. Then we can execute some rather arbitrary code on these device buffers using the compute capabilities of the GPU. And then in the end, we can map data back from the device memory to the host memory and move the updated chunks of data back to the host memory. Okay, so this is roughly how things work in OpenMP. All right. This is the syntax. This is more for a reference. I will not go through this in very much detail. You'll see the syntax explained in example, but this is more for your reference, and there will be a bunch of those slides in our presentation so that you have the full syntax. All right, let's come back to our saxpy. All right, so as I said, initially we wanted to offload the blue part, which is now indicated in black here. And what we want to do is we want to offload that loop to the target device. So all I did is I replaced the OpenMP Parallel 4 directive with a pragma OpenMP target, right? And so what happens is until the host thread reaches the OpenMP target directive, the host thread is executing. Once it hits the target directive, it transfers control over to the target. The target starts executing the loop. And when the loop ends, so this is now down here at this location here, the control comes back from the target and the host thread resumes execution, executing the second part of the green code. And the way you can compile this, you'll see a couple of command line syntaxes scattered across this presentation today, but pretty much for AMD GPUs, this is an Radeon Instinct card of current generation, or MI100, if you will. So this is the command line that you need for the ROCmCC or the AOM compiler to produce code that offloads this target region to an AMD GPU. All right. Now, the question is, what happens with the data, right? So here, we're accessing Y, we're writing it, we're reading it over here, we're reading X, and we're reading A, right? So what happens to the data? Now, the good news is, the way I defined the saxpy, I have a definition of Y that says Y has this many elements, right? And what the compiler is now able to do, and also supposed to do, my clicker isn't working anymore. What I have to do now is, or the compiler has to do now, is it will look at the code in your region, right? It will identify the data that you are accessing, in this case, the Y array. It will find the definition of the Y array outside in the host code and infer automatically what number of data elements it has to transfer. And so what it will do, it will kind of add what I was showing on an earlier slide, these map clauses to transfer the data, in this case, the Y array, to the device and from the device, right? And it will do that for all your arrays and scalar elements or scalar values that you're using. So the same will happen for the X array. I'm not showing that for the sake of not convoluting the slide too much, but pretty much you can think about also a map to from clause being added for the X array. And so what happens then at runtime is that since the compiler identifies the arrays automatically, it will automatically transfer the X and Y array from the host to the target. Before the offload happens, then it will transfer control. And in the end, before it passes control back to the host thread, it will transfer X and Y back from the target and store it in its original host locations. So there are two things that you may see, right? The first is copying X back is not really necessary. Right? Actually, it's one thing. Sorry about that. So copying X is not necessary. It wasn't changed, right? If you look at the code, you'll see that we are only reading X, but the compiler will still transfer the unchanged X array back from the GPU. So this is something where a smart OpenMP implementation could actually be smart enough to figure that out, but we are not requiring the compiler to further analyze the code in here to understand if an array is actually changed or not to avoid this additional data transfer back. The other thing that I have to tell you is that the map clauses that we are adding here is a so-called presence check. So what the compiler will automatically do, and we'll resume that topic in the next webinar actually, is that it will only transfer the data if X and Y haven't been allocated before. You will not know after this webinar how this can be done, but just take my word for now that we'll explain it in more detail in the next webinar, that there's some magic in the back so that things turn out the right way. Okay. All right, in Fortran, it's pretty much the same way. So again, the compiler will do the same thing as in C. So it will look up the usage of assumed size and assumed shape arrays. It will try to find the dimensionality of those data objects. And then if it can find it out, it will automatically do the same kind of transfer that I was showing earlier on the previous slide. And again, you know, this map to from, and that box should actually point here, that map to from is again a presence check. So if X and Y are already present on the target device, no extra transfer will happen. All right, now in case you want to avoid this extra transfer of X, you can then be more specific, right? You can now overrule the decision the compiler has made to do a presence check for map to from, and augment the code manually by saying, okay, the X array, I know that it's only being read on the target device, so you don't have to transfer it back. And then you can add the appropriate map clause, like I'm showing here on this slide, to avoid this extra data transfer. The other place where you actually need the map clauses is anytime the compiler is not able to infer the data size. So in this particular example, what I changed is now it's the real saxpy where the X and Y array are coming into the function as C pointers. And then there's an additional argument for the size of those arrays. So that's kind of a typical formulation of this algorithm. And now what happens is the compiler will look up the, will see that Y is used. It will go back in the function code to see that, okay, Y is coming in as a float pointer. And so now the compiler doesn't have any size information associated with Y. And now the compiler will not be able to infer how much data it needs to transfer at runtime. And in this case, the compiler will actually tell you about this, and then you will have to add the appropriate map clauses to tell the compiler, okay, please transfer the Y array to the device and download it again after the offload happens. And you have to transfer from the zeros element with SC number of elements that you have to transfer. And what we did in OpenMP is we invented a syntax that is similar to Fortran array notation to describe data sizes in OpenMP directives. And so in Fortran, you would read from the zeros element to that element. And in C, we follow the typical C semantics that the array is defined by the number of elements and not by the highest index in that dimension. So this is actually the number of elements that is transferred in C. And in Fortran, it would be the highest index. All right, and so we already had this kind of as a question in the chat window. The target construct is actually something that transfers the control flow to the target device and does so in a sequential and synchronous fashion. Okay, so everything I was showing previously, like here, right? The gap here was actually intentional. So the host thread will actually wait. It will not continue execution until the target device has finished execution, right? So that's the first thing. The second thing is that everything I was showing for saxpy so far here was kind of sequential, right? So we basically launched a single thread, and thread has to be taken in quotation mark because the definition of a thread is typically different from an operating system thread. at least for something like a GPU. So we were launching one thread only on the target device executing that loop. So we didn't really make use of the capabilities of a GPU yet, right? Now, what looks like a mistake that we made in OpenMP is actually very, very intentional. If you go back to the execution and the device model, I said that pretty much everything that satisfies rather flexible boundaries, like a device that can receive data from the host, process the data, and then send data back, is a valid offload device. That kind of not only includes GPUs. If you remember the history of Intel architectures, you will find that there was a processor-like offload device called Xeon Phi, right? That had different capabilities than a standard GPU at that time. There are FPGAs, right, where you can that satisfy the OpenMP offload device model. So taking that flexibility and designing a language around that flexibility meant that we had to separate the concerns of controlling how data and control is flowing between the host devices and the offload devices, and the other concern of describing how to create parallelism and in what form to create that parallelism on this target device, right? So this is what we did. So what you have to do as an OpenMP programmer, and this is actually different to OpenACC or OpenCL, CUDA, HIP, and all other offload programming models. Programmers really need to explicitly create parallel regions on the target device, right? The target constructs only are there for managing where data resides and how the control flow flows between offload devices and host, right? And then you combine those with the right type of OpenMP directives that you need for a particular device to create that parallelism for that particular device. So in theory, you can combine this with any OpenMP construct, right? For something like a GPU, we will have like data parallel or loop parallel constructs. But if you have a more capable device like the Xeon Phi coprocessor was, where you could actually do regular OpenMP tasking, you could use OpenMP tasking inside an offload region to make use of these additional device capabilities, right? But you know what you probably already inferred from what I was saying, that there's only a useful subset of OpenMP features for a target device that makes sense to be used on that target device, right? That's not a limitation of OpenMP, that's a limitation of the offload device, right? So if you have an offload device that doesn't support OpenMP tasking, you simply can't really use it, or you can only use it to a limited extent, right? But the same holds also true for something like I/O, or you know, sending messages via MPI over the fabric from a GPU. You know, there's kind of there are restrictions that are in place just because of the nature of the architecture that we have to deal with. All right, with that, you know, let's complete saxpy.
Michael, there was a
Yes.
question. Not sure if you if we should add more detail. So there was a question: what happens with unified shared memory? And I basically said that if you make use of that feature, which basically correlates to the use of a different programming model like CUDA or so, you have to tell OpenMP about that. Is there anything that you would like to add at this point?
Yes, just probably a tiny bit of summary of what we will cover next webinar. So the way OpenMP is specified is that you have seen the places where the compiler can infer the map class, and you have seen places where the compiler cannot infer the map class, and then the programmer has to add it. Now, as you rightfully discussed in the chat window already, if you have unified shared memory, then you don't actually need those map clauses, because the hardware or the implementation, say a software layer, will take care of managing the data transfers in the back in a kind of a transparent way. from an OpenMP perspective, you will still have to add the map clauses, even though you don't need them. And so what you can do in OpenMP is there's a directive called requires, where you can tell the implementation that your code is with, basically you can say your code requires unified shared memory because you did not bother adding the corresponding map clauses. And then the compiler has a way, or the implementation of OpenMP has a way to say, well, my implementation and my architecture that I'm compiling for will need the map clauses, and then it will error out on your code. And an implementation that supports unified shared memory will then say, okay, you know, now I know by this requires directive that I don't have to expect any map clauses in the code, and that the programmer potentially didn't write them. And so, you know, you kind of modify the default behavior that I was explaining earlier. And then you can still add the map clauses kind of as a performance optimization mechanism. Yeah, let's leave it there, because otherwise we don't have to talk about unified shared memory in the next webinar anymore. But we will cover that in a bit more depth in about 4 weeks. I hope that answered the question. Okay.
Yes, and maybe.
Yeah, go ahead.
Again, maybe that there was a little bit of confusion. So I explained the target transfers the control flow, but you said it in a way that this is only synchronous. Yeah, and
Yes.
I said that we will look at asynchronous offloading in the next webinar.
Yes.
By default, it's synchronous, and I basically said we start with the basics here, and we can tweak the performance, for example, by enabling asynchronous offloading, and we will explain that in detail next time.
Perfect answer. Thank you. All right. Okay, let me finish my last slide, and then Christian will take over. So I still owe you kind of a parallel saxpy, right? So here it is. So what I did is I have my you know, the OpenMP target constructs with the appropriate map clauses. I'm not assuming unified shared memory here. And since that thing was transferring synchronously, but also only create a sequential thread, I'm doing the regular pragma OpenMP parallel for SIMD that you already saw in earlier webinars, and that will create you know, parallelism on the GPU device. All right. So what happens is it creates a teams of threads to execute the loop in parallel using SIMD instructions should they be available. Now the thing is, and this is now something that Christian will explain to you, GPUs are multi-level devices. So they not only have SIMD and thread, but they may also have thread blocks. They may even have sub-devices and all that kind of beautiful things that make GPUs highly parallel and highly performing devices. And so Christian will now explain how you can deal with those devices in OpenMP. All right, now I need to stop sharing. And Christian, you should be able to share.
I'm working on it, don't worry, sorry, too many windows. And okay, do you see my slides?
Yes.
Thank you. Okay, so Michael explained the offloading or the data flow, or sorry, the control flow. And now I would like to add some more details on how to actually express parallelism on the GPU. And I believe in the very first webinar, when we gave an overview about OpenMP and motivated why OpenMP supports work sharing, tasking, vectorization, and offloading, I said something like, this is an advantage because you can reuse the concepts that you already know. And that now means, and we'll have a closer look, that to some extent, in order to express parallelism on a GPU, we will actually make use of the constructs that you already know. However, there are also some new constructs which are specifically designed for the way GPUs are being constructed, or the memory hierarchy that you can find on a GPU. I think that's a better term. And this is why we are going to take a look at the teams, distribute, and a little bit later on also the loop constructs. So teams and distribute are new, and these have been introduced with a special or with GPUs and their current architecture in mind. And in a few minutes, we will see that we can actually combine those, or we have to combine those with parallel and parallel 4 or parallel do, depending on your programming language. So before we start, I have to get the terminology right. That means I have to introduce 2 new words. You already know teams. Team. That means the OpenMP team that's executed or that exists within a parallel region, and that's a team of threads, including the initial thread that's, for example, available to execute work sharing constructs or execute tasks. Now, because of the special memory hierarchy of a GPU, we cannot get the full performance of such a device if we have only one team. And this is why we need multiple teams. And I'll add more details and hopefully a very good illustration later on. So on a device, and possibly also on a host, but more specifically on a device like a GPU, we have to make use of a so-called league, which is a set of teams. Each team is what you already know, but you want to have multiple teams, for example, to get the thousands of cores busy that you have on a GPU. And in order to create a so-called league, which is a set of teams, we have the so-called teams construct. This is new. Yeah? The other term that we need, and basically it's also a concept that you have to understand, is the so-called contention group. And a contention group is a thread of a team within a league, and their descendant threads, and all the threads within a contention group can synchronize together. Threads outside of a contention group, for example, are not affected by a barrier. So the barrier or any other synchronization construct applies to this so-called contention group. And we have multiple teams on, for example, on different devices, or the device and the host. Yeah, they do not synchronize with each other. That means, as a simple example, if you encounter a barrier on the host, this will not make the threads on the device synchronize or stop with this barrier, because we have different contention groups here. I think this is what Michael already mentioned in his description of the control flow. So league is a set of teams. The teams construct creates this league of thread teams. And the idea is, as I said, to have multiple teams available on a GPU to execute your code. And again, a team is what you know. There's an initial thread, which we tried, let me use my pointer here, which we tried to mark in blue. And then there are I think I called it worker threads in the first webinar, which have this brownish, orangish, whatever color. It's not quite clear to me here. However, a teams is a little bit special because only the master thread, I think this should read the initial thread of each team, executes the team's region, this blue one. So let me be clear, the teams construct creates this league, the set of teams. It contains a structured block, which is this region, that means the code within the teams construct, but only the the initial thread is then active. The other threads are there and available, but as you will see later on, we need additional constructs to actually involve them in the work. The number of teams can be specified by the so-called numTeams clause. So you can ask the compiler to create 23 teams on your device, or you can leave compiler and runtime, I think runtime is the right term here, to choose freely what is the right degree of parallelism here. You can also determine how many threads will be available within the team by using the thread limit clause. And the threads within the different teams cannot synchronize with each other. So that means if we have a barrier, that's only part of this team. And this is not, or this follows our definition of a barrier and the parallel region and the force from the first webinar. Technically, you can also make use of this functionality on the host, but not all implementations support that, and in particular, they do not always support that efficiently. So this is really or has been designed and first implemented for the devices. Now, what can you do with a team? There are special OpenMP constructs and to some extent routines, that are available to be used within a teams and possibly only within a team. So the first one that we are going to look at the following slides is a distribute construct. The distribute makes use of the fact that we have multiple teams and there's only the initial thread within each team active. And then we can partition loops among the teams that are available, and more details and in particular how that works for the saxpy operation later on. We can combine this distribute with a SIMD, you already know that. We can combine the distribute with a parallel, you already know that. And we can combine the distribute with a parallel SIMD, you already know that. So here we are reaching the territory of OpenMP that we have already explored. We do not have to make use of the distribute. We can also use the teams construct with a parallel and then parallel for, parallel SIMD, and so forth. So that means we would have multiple teams. And then if we say pragma OMP teams parallel, we would have, we could involve the other threads within the team so that we have a parallel region as we know it. The initial thread and the worker threads all active and working on the for or do work sharing construct and so forth. And then there's OMP get num teams, similar to OMP num threads in the wording, and OMP get teams num, which is the ID of the team, again starting with 0, going to n-1 if you have n teams on a certain device or on the host. Now let's take a closer look at the work distribute construct, and then I'll start putting both together and explain actually how to express parallelism on a GPU for our saxpy example. So I said, if we have multiple teams and just using the teams construct, only the initial thread is active. And now with the distribute construct, we can partition a loop among the teams, which is very similar to work sharing among the teams region. So if we have a loop with a certain number of iterations, we can partition the loop so that each team's initial thread executes a subpartition of the loop iterations. In many cases, very similar to the OMP4 construct, where each thread executes a subpartition of the iterations of the corresponding for loop. So the limitation of the distribute construct is that it has to be strictly nested inside the teams region. So you have to say pragma OMP teams distribute or pragma OMP teams and then pragma OMP distribute in the following line. And then there has to be the for loop to which the combination of both constructs applies. With distribute being designed for a GPU, there's no implicit barrier at the end of the construct. So remember that synchronization on a GPU is much more expensive, relatively, than synchronization on the host. And this is why there's no implicit barrier at the end. And this is why it's not a work sharing construct. And then finally, you can also influence the scheduling. I think the only scheduling kind is static at the moment, but you can specify the chunk size. If you do not do that, then it's very similar to the static. So that means compiler and runtime can do hopefully can select hopefully a reasonable choice for the specified target architecture. Not sure, Michael, if there are new schedule kinds introduced with OpenMP 5.1. I didn't check, but I believe it's only static at the moment.
No new introduced.
Thank you. So let's go back to the saxpy code. This is slightly different from what Michael was showing. It's doing the same thing, but I might have a different coding convention here. So this is daxpy, the routine, y equals a times x plus y. And so daxpy is using double. Saxpy would use single precision. Okay, this is the main routine, and the code is allocating data for the arrays. Allocating memory for the arrays x and y. Both have the dimension of n, so it's reasonably large. A is a constant. We initialize the arrays x and y with some values, and then we invoke the kernel, so we call saxpy. N is a dimension, x and y are the two arrays, a is a constant. Then, of course, we have to check if the computation was correct. This is not shown here. Then we have to free these arrays and can return success. I think by now you should be perfectly capable of parallelizing this for the GPU. For example, for 20 cores, you would say here pragma omp parallel 4, and that's about it. Yeah. Or now our challenge is to parallelize that for the, let's say, 5,000 cores that we would find on a modern GPU. And of course, we also have to manage the data environment. So that means X and Y, and to some extent also A, have to be present on the GPU. How do we do that? Well, we need some things that we already know. We have available the target construct, which actually performs the offloading of a kernel and also can help us in managing the data environment on the device. That means we have to map X and Y. We need teams, parallel, distribute, and for in the following example. So teams to create this leak, distribute to partition the loop among the teams, parallel to actually have a parallel region, and for then to actually have work sharing within the teams on the device. Do would be the same or the equivalent for the Fortran programming language, and SIMD is something that we're not going to make use of, but we could add it here. And I think for the saxpy kernel, there's a little difference in performance. Yeah. If you want to get good performance, in particular for the homework assignment, you should also think about the collapse clause later on. Okay. How do we compile for the target architecture? So I'm sorry, I only have access to NVIDIA GPUs available in Aachen, but I think Michael had the compiler command line for AMD GPUs on one of his earlier slides. And in theory, there's only a little difference. So I'm using the Clang compiler here. I'm saying -f OpenMP to enable OpenMP support. Let me add the note on the recent Clang compiler version. So I would recommend, if you want to program for a GPU, to use always the latest and greatest release. So in particular, the GPU support and the OpenMP offloading support is undergoing significant changes in a rather short amount of time, which for many programs results in significantly improved performance and also capabilities. So I was preparing the example that I will talk about later on with Clang 11. Since then, Clang 12 has been released. I didn't check that, but I think a Clang 10 release would have not worked well with my example that I'm going to present. Sorry, with a homework assignment that I'm going to present later on. Yeah? So really use the latest and greatest that you have access to. If we want to program for GPU devices, we have to say -x OpenMP target to enable the OpenMP target support. Otherwise, the target construct will just be ignored and the code will be executed on the host unless this becomes, for whatever reason, impossible. Now we have to specify the target architecture. So f OpenMP targets means NVIDIA PTX 64-bit, whatever, NVIDIA CUDA. So this is the string that you have to pass for NVIDIA devices if the CUDA software stack is correctly installed on your GPU. NVIDIA PTX means this is a native code for this NVIDIA devices. 64-bit is the addressing scheme and so forth. Yeah? And you see it's f OpenMP targets. That means if you want if the compiler supports multiple devices, you could add a comma-separated list here. And then in theory, the compiler would generate support for multiple devices and select the right code at runtime. That's not perfectly implemented at the moment, but this is clearly how it will be available in future releases. So you could write code that both supports NVIDIA and AMD. We have to specify the target architecture here. I have to excuse, I don't know what that means in the NVIDIA terminology here, but this is what you have to specify, for example, the Volta generation of these devices. On some installations, you have to specify the CUDA path. On some, you do not have to do that. And this is our source code. Okay. Good. Yeah, let me say this target device specification is optional, but it results in better performance. Now, this is our code. And the only change that I've made is marked in red here. I used what Michael has explained, pragma OpenMP target. And with it, I basically say, compiler, please do some magic. Do you believe in magic? No, you should not. Yeah. So I think Michael explained most of that already, but on this concrete example, I would like to explain what's happening here. So here we ask for just this compute kernel to be offloaded to the device. What the compiler will do is generate codes so that this can be executed on the GPU. What the compiler will not do, because actually it cannot do that without additional information, is to make sure that the data is being transferred to the device, because we have forgotten, or we did not add any map clauses in this particular example. So if we execute this, this is on my cluster, the compiler, and this is on my cluster, the flags for OpenMP offloading for the target device in the system on which you're compiling. This is what I've showed on the previous slide. This is the source code. I execute it, then I get the failure. lib OpenMP target fatal error 1, failure of target construct while offloading is mandatory. Is this a reasonable error message? No, but error messages are also improving with compiler releases. So Clang 12 might give us a better answer, but I have to admit, I didn't check. So it says failure of target construct. So something was wrong here, while offloading is mandatory. So we asked for the compiler to perform the offloading, and we specified an OpenMP target construct. So it basically says, you asked me to offload, but something went wrong. Now it's your turn to go debugging. And this is, there are limits to what you can do. In particular, sometimes, I'm just telling from my experience, if you get this error message, it might also be that the GPU is in unusable state. So you have to reset it, reboot the node, and so forth. If that happens and you're sure you did everything right, then sometimes you have to talk to your system people to reset the GPU node. However, here in this code, it's clearly my fault. So there's no compiler error, but I would call it a cryptic runtime error. It's not really cryptic, but it didn't help us any. It didn't really help us. So there's the NVIDIA profiler. You can think of what the so this tool is not made to debug, but I just wanted to show you what's happening if we execute this code with the NVIDIA compiler, and it basically says it's profiling this process with ID so and so forth, and nothing was profiled, because there was no successful offloading. We can also use the CUDA memcheck, which is a tool particularly designed for CUDA, but it supports any code that runs natively on the GPU. And this gives us some clue. It says there's an invalid global read. Global represents it's trying to read from shared memory of size 8. That's 8. That's a double precision variable in routine, and that's OpenMP offloading. Thank you very much. saxpy. So this is what our compiler generated out of our saxpy routine by thread so and so and block so and so. Address so and so is out of bounds. So it's not perfectly clear as an error message, but it indicates that there's a read that's invalid, and that can give you a clue that actually the data is not present on the device. Out of bounds could mean that there's that you're accessing more data than has to be mapped, and that's a usable error. That's then a error message, but in many cases, or in our case, sorry, on the previous example, there's basically nothing added here. Good. How can we fix it? I think many of you knew already. So we need the y variable. It has been initialized here. So we have to map it to the device before the target kernel is executed. And we also have to make it back from the device because we want to check the values, that means the result, afterwards. For x, we only have to map it to the device because it's a variable that has been initialized on the host. We don't need it afterwards. So the GPU can, or the data on the GPU can be destroyed or technically overwritten in the next kernel. And here I'm also mapping the scalar variable a, just for the sake of completeness. Now, do you think this code flies? Unluckily not, but it works correctly. So there's no error. That means all values are 4. But the execution time is 102.5 seconds. For comparison, on a single CPU core, and I have to admit I didn't specify the CPU. I think it was a Broadwell CPU, but I'm not 100% sure. But more or less a recent CPU, this was only 0.12 seconds. So it's more than 2 orders of magnitude slower. Something going wrong here. So what happened? I only said pragma-omp target, and this will offload this kernel. This kernel will be executed then by one thread. And the only thing that the runtime can do is to map this one thread onto one core. On the host, the core is perfectly capable of executing this code reasonably fast with all the caches, out of order execution, and so forth. Not going into detail here. But on the GPU, the performance only stems from a large degree of parallelism and to some extent also from vectorization, or let's say means SIMD execution. So with what we just specified, the single target instance, we can't hope for good performance. Now let's try something else. We say pragma-omp target parallel 4. We already know that. So that means now we have more than one thread available because the runtime can generate a team of threads. The same mapping. So what I'm only changing here is I added the parallel 4. Okay, the data environment management remains the same. Do you think this flies? It works much better. So we're down to 9.65 seconds. Let me illustrate what's happening here. This is what we had before. Now we have a team of threads. And I think this NVIDIA terminology here, sorry for that. We have a so-called block. I would call it a team of threads. So we have multiple threads. What can that be mapped up on? Well, let me go back one slide again. Remember, parallel has a barrier at the end. So we have to wait for all the threads. And also the 4 has an implicit or implied barrier at the end. So the compiler and the runtime can't do magic. They have to follow our orders. And I think we said that in the first webinar. So we ask, maybe as a side effect, but we ask for this synchronization to happen. We ask for synchronization here at the end of this parallel for loop. So that means we can only map it to a single multiprocessor. And now this is a part of the NVIDIA GPU. And I'm sure AMD has different names for that. Not sure if you can jump in here, Michael.
Sorry, say that again.
So what's the equivalent of a multiprocessor or a streaming multiprocessor on an AMD GPU? I don't have the term here.
Probably the closest, well, we don't really have that. The closest probably is going to be a compute unit.
A compute unit. Yeah, that's a reasonable term. Thank you. Okay, so why can we only use a multiprocessor? Well, we have to implement the synchronization as implicitly asked for by making use of the parallel 4. So each block, that means a parallel region, means in correspondence a team of thread, is executed on such a multiprocessor. So only concurrent teams or blocks can then fully utilize a GPU, because this is the only domain in which we can do the synchronization, I think I said. So how can we achieve that in code? Here we are. Now we are going to make use of the new constructs that I introduced earlier on. So we say pragma target, teams distribute, parallel for, and then the mapping. Sounds like a long construct, but we need all that. So let's remember what this does. The teams creates a leak, means a set of teams. Yeah? Distributes a loop iteration of the following loop among the teams, but in such a way that only one thread within each team, basically the initial thread of the team, is active. And then the parallel for makes sure that, again, of this loop, the other threads kick in and they all work on jointly on the for loop. So we didn't do anything on our code. We still use parallel for to actually distribute the loop iterations within a team. But now we have multiple teams, which has a slightly different semantic because there's no implied barrier at the teams and distribute. Now we're down to 0.8 seconds. And this gives us the opportunity to have a kernel that consists of multiple blocks. These are the multiple teams, each within a parallel for. And we can execute each block, kernel, whatever you might want to call it. In my OpenMP terminology, the target is the kernel, but we can execute each of them on an individual multiprocessor device. We have the barrier within the multiprocessor, but we can fully utilize the GPU. Okay, let me go back one slide. Now the total runtime is 0.8, while I said on a single core on a GPU it's 0.1. Is this now a glorious result? No, but you have to understand what we're doing here. This is a rather small array, and we're just executing this operation once. So that means doing it straight on the host is obviously much faster, because doing it on a GPU means we also have to do the mapping. That means we have to transfer data from the host to the device, namely Y and X. And at the end, we have to transfer data from the device back to the host, namely Y. So if we would exclude the data management from the runtime measurement, then the GPU would be significantly faster. But for our whole program to be completed, we obviously need the data management. Otherwise, the kernel would not be able to be, could not be executed. So if you do a single task on GPU, you have to understand if it's worth making use of GPU. If you would execute the saxpy multiple times and being able to keep the data on the GPU, then doing this code on the GPU would be faster. So saxpy executed only once is not a good example for making use of a GPU, but the code is short enough to fit onto a slide, and we can explain why we need the teams distribute parallel for effort to actually increase the degree of parallelism available on the GPU. Good. So this is a summary of the teams construct. Num teams, thread limit, this is what I explained. We can ask for certain defaults. You already know private, first private, and shared. We can have a reduction clause. You know already about that. We can also put the reduction onto the for construct, of course. And we have an allocate clause, which is an OpenMP 5 feature of memory management. So that means we can make use of special kinds of memory. And this is a summary of the distribute construct. Again, it applies to a loop. First private, private, last private. You know that this schedule is what I introduced already. And then there's also the collapse clause. So that could ask, or that would ask the compiler to join multiple loops together, or technically to fuse them and then apply the teams distribute to the fused loops. Okay, how am I in time, Michael? Is it okay, or am I too slow?
10 a.m. So perfect.
Okay, then let me go to the loop construct, but this is only very brief, something very briefly. Anything that I should discuss regarding the chat, or did you solve that?
There is probably a question, even though it doesn't really hit the topic, but I answered it. So there's a Jupyter kernel for C++ based for, so that you can do C++ programming in Jupyter notebooks, that Cling thing. And I kind of recall that you guys are working on something similar to show OpenMP and teach it. Can you quickly spend a few words on it?
Yes, so we modified Cling and we modified the infrastructure, which is XOIS, which passes the data between the web front end, meaning the notebook, and the back end, meaning Cling. And we fixed a few things so that Cling does support OpenMP. Yeah, so we enabled the OpenMP compilation and added the runtime there. And this was done by a student of mine, Jonas Hahnfeld, and he, I think, end of last year, joined the team at CERN that's actually developing Cling. So I didn't quite get the question.
No, I think
the
that's
question
a good
was
answer.
maybe just if GPU part is also supported.
Offloading, you mean? No. So in Cling, at the latest release, offloading is not yet supported to the best of my knowledge, but this is on the agenda. So the reason for that was that the Cling release was based on Clang version, I don't quite remember, but that version has almost no support for offloading. But the next release for Cling, not sure when that is due, is rebased on a recent version of Clang, and that means GPU support will be available.
Thank you.
Okay, cool. That's it.
Yeah, if you want more details, I'm happy to follow up. Send me an email if you like. So there's a final construct, the loop construct, that I would like to introduce here. So I explained Pragma OMP teams distribute parallel 4, and we might have added the SIMD here. But now sometimes it might be reasonable, and I can understand it, to shift the burden of selecting the right constructs and also some clauses. Here I just asked for the defaults by the runtime and so forth, to shift the effort of selecting constructs and clauses to the team of compiler and runtime. So with OpenMP for many years, or for many releases, I think that's a better term, OpenMP was pretty prescriptive. I hope I selected the right word here. That means OpenMP, or the individual constructs and clauses, had a very detailed semantic. And that means there was a clear expectation of what happens when you say teams distribute parallel 4, for example, and I explained that. However, OpenACC brought up, let me call it the descriptive approach, where you basically say, this is what I want. I want this loop to be executed in parallel on a GPU. Please, dear compiler and runtime, do the right thing. There are advantages to both. So if you're an expert, you might want to have full control. If you are a novice, you just want the thing to be happen in the right way. So neither is better or worse than the other approach, in my personal opinion. But OpenMP didn't have support for this descriptive feature, and that means the language committee in OpenMP aimed to add support for that. Now we just can't change the semantics of the constructs, clauses, and so forth that we have in OpenMP. And this is again why we needed new clauses to also provide more freedom. So OpenMP remains backwards compatible. That means the constructs that we have will remain to exist, but we wanted to have more support, and we wanted to have also support for descriptivity. And I have to admit, I like to confuse prescriptivity and descriptivity. Basically, that doesn't translate for me well. I hope I did it right. Otherwise, Michael has to jump in and correct me here. So in unless I confused myself again, the loop construct is the first step to introduce descriptivity in OpenMP. What does it do? It basically specifies that the iterations may be executed concurrently. That's all. And that's a more relaxed specification than, for example, a parallel for, because a parallel contains a barrier at the end, the for contains a barrier at the end. The loop iterations have to be partitioned into chunks. Chunks have to be executed by threads in a certain order, and so forth. Yeah? This is a much more detailed prescription of what has to happen than with this new loop construct, where it basically says that all iterations may be executed concurrently. So that means, for example, that the iteration 2 might be executed in this by the same thread, but after execution iteration 1. This would not be possible with a for construct. And this degree of freedom in what is allowed enables, that means permits, the compiler to generate threaded and or accelerated code, and enables, that means permits the runtime to hopefully do the right thing on a device. So again, this is my way of approaching this here. If you want to start quickly on a GPU, the loop construct might be a good thing. And if performance is good, then you're lucky. If performance is not so good, then you have to understand what's going wrong. And in many cases, then you have to go with the traditional constructs in OpenMP. And that means the constructs I just explained to make sure that the compiler is doing the right thing. So again, I don't think either the loop or the other target teams distribute parallel for is better or worse. It always depends on your code, on your compiler, and what you want to achieve and what you're willing to invest. So pragma OMP loop is the construct that again applies only to for loops. And I think you know the collapse clause, you know private, first private, and reduction. This is all well known. Now, because the OpenMP team is language committee is a funny committee, we added the clause ordered with the option concurrent, and this is a default. So this is only there for future possible extensions, because concurrent is a current default. And then there's also the bind clause, which defines, I had a hard time specifying that, it determines which parallel execution entity will be used. So at the end of the day, will it be a Teams construct or a parallel or a thread construct? I'm not sure if Michael has a better one sentence or definition of what the bind construct does here. Sorry if I interrupt you here.
Not really, but you know, if you think about a GPU, that is the way to specify how much of your GPU the loop construct should span, pretty much.
Yes, thank you. This is what I try to express as parallel execution entity. I don't have a better term here, because there are different CPUs, different GPUs, and so forth. Good, and that's about it already. And you can replace parallel, target teams distribute parallel for with a target loop, bind teams, and then experiment with your code what kind of performance or what level of performance you actually get. Questions on this?
One question, does the loop construct also handle all the data dependencies? So it does transfers and all the things?
So it's limited, so it doesn't do a whole program analysis. So that means for simple kernels, it performs, for example, the offloading of scalars, but in the example above, it's not deducible for the compiler what data has to be transformed, so that transferred to the device, if we're talking about a GPU. So that means at the end of the day, in almost all cases, you still have to do the data management with target and map clauses. Yeah, I wasn't specific on that. Very good question. Yeah, so it can't do magic. So for example, in the saxpy case, for the compiler, it's not possible to determine the size of the arrays X and Y. Yeah, it could guess that it's of size N, yeah, but there's no way to understand how much data really has to be transferred because these are pointers.
Yes, plus you will still need the appropriate target construct to tell OpenMP to move over to the GPU. Right, so the loop construct is, if you will, just another way of specifying how you want to create parallelism,
Yeah.
but you still need to have the, the control constructs that indicate where the data is residing and where the control flow is.
Yeah, I think in my example, I only said pragma omp target loop. Yeah, I should say pragma omp target loop, map 2 from Y, and then map 2 A and X. That would be the translation of the teams distribute parallel 4 to the loop. So I forgot that. And, so this is why it's a good question. Yeah. So there's a Fortran question. Michael, you answered it. Thank you. I'm not capable of answering this Fortran question.
Yep, I'm the dinosaur.
Okay, so that would conclude the content that we have prepared for today. So we're a little bit faster than previous webinars. And we have a couple of hands-on exercises to familiarize yourself with what we have talked about so far. And in the chat, we already made a few forward remarks. So in the next webinar, we want to talk about asynchronous offloading, unstructured data movement, and so forth. We didn't want to put everything into a single presentation. Michael, anything to add at the moment? Otherwise, we would go on.
There are two questions that, well, there's one question that we should probably answer right now. So how widely supported are today's various features, most notably loop? And then there's another one that it kind of ties into that. Let me scroll back up. Can you let us know when you discuss some features which are not widely supported? For example, support in the Intel One API compilers, AOCC, NVIDIA HPC SDK, Cray, IBM, and so forth. So that's probably a bigger question about how widely supported OpenMP is today. You want to make a first attempt and then I'll summarize?
So I have to admit, I don't know exactly what is supported with respect to the loop construct. Yeah? I can only say that the Clang compiler in releases 11 and probably even better in the recent release version 12 is really, really good. So it works on x86 with different GPUs. It works on ARM and Power with different GPUs. So in many cases, you will get good performance. However, there are always some applications where whatever, the PGI or NVIDIA compiler or OpenACC or in particular CUDA or whatever you might want to use for your GPU, be it OpenCL, and this program model can deliver better performance. Yeah? But I think it's robust enough to give it a try. That was different 1.5 years ago, yeah? No question, but this has changed over the last few years. That's our opinion. So we have several codes with GPU support compiled with the latest Clang in production on our systems. That would be my statement.
Yeah, I mean, for the compilers, the problem is for us as the OpenMP ARB that this is really a moving target with, in general, some very interesting release timelines by all the vendors. So we just can't keep up with the many releases that that OpenMP vendors are making. I do know from previous GTC that NVIDIA's latest HPC SDK seems to have a compiler that already supports the loop construct. I do know that Intel is working on it, so is AMD. So there's various degrees of readiness here. This also, by the way, applies to other OpenMP 5 and 5.1 features. So most vendors are still catching up on the big release that the OpenMP ARB has made with OpenMP 5. That is a lot of work to get it implemented. And then it's even more work to get it implemented in a high quality, high performant implementation. So the best way to find that out is to just, ask the vendor of that compiler or OpenMP implementation. And as a starter, you can have a look at the tools webpage at openmp.org, where we also try to catch as much feedback from the vendors in what they support, which level of OpenMP, and what specific aspects users need to be aware of. There's a follow-up question. Is there a Fortran compiler supporting these features for NVIDIA and AMD and future Intel devices? Clang cannot be used for Fortran. Is Flang already supporting OpenMP 5.0? Up to which version of OpenMP? Yeah, that's a bit difficult, as I said. So I cannot really speak for Intel and NVIDIA compilers, of course. So the AMD compilers support pretty much everything of OpenMP 4.5, with some extensions that we already made for OpenMP 5. So for instance, cross-device reductions seem to be working in our compiler quite well already. NVIDIA, as I said, already has the loop construct in there. I do know that Intel is also working on at least partial OpenMP 5 support for GPUs as part of the One API initiative. And with respect to Clang and Fortran, the way Clang works right now is, so the upstream version of Clang, so this is the initial LLVM project, they do develop a new Flang front end that they right now call F18. My last understanding is that they don't support all of OpenMP, rather restricted subset. That may change quickly though. So, as I said, things are changing more than I can keep up with the changes. And most vendor compilers, so as far as I understand, NVIDIA's, AMD's, are based on the old Flang frontend, which pretty much is the Fortran compiler frontend that I believe PGI released as open source to the Clang community. And F18 is now a rewrite of that frontend for upstream Clang. And then the Intel implementation uses the iFort front end and then has a LLVM based backend. So they're going a different direction by using their own, I think they call it now classic Fortran compiler. They kind of take that front end of that compiler and use it on top of an LLVM backend. So that's roughly my understanding of the community and the compiler implementations that I'm aware of. Yes, there is an OpenMP Fortran compiler for AMD GPUs, and that's the AOMP compiler that just has released the version 13. And then the production compiler is the one that ships with ROCm, which also was released like 1 or 2 weeks ago as version 4.1.1. That ROCm stack also contains a Clang-based compiler, and that Clang-based compiler has a Fortran frontend as well. Is NVC also Clang backend? Yes. Pretty much every compiler these days is Clang-backed. It's a trend in industry right now. Okay, Christian, let's go for the hands-on exercises.
Yeah. So something's wrong here with my window. Okay, actually, we have 2 exercises prepared. So, Michael, I hand over to you.
Yes. So the one that we're gonna start with, kind of to warm you up, guys, is the stream benchmark. It's infamous. It just measures raw GPU, in this case, GPU memory bandwidth. The way we designed the code is we took McAlpin's traditional stream. I slightly modified it to use mallocs, and I already implemented like compilation guards and the functions that have GPU in their name. So you can pretty much, with a compiler flag, decide if you want stream for host or GPU. Just look at the makefile and it's probably self-explaining. And so the task that you have to work on, or that we're asking you to work on, I should say, is to add the proper target directives and data mapping clauses at the 4 functions for the copy, the scale, add, and triad benchmark. The thing that you will see, though, if you just use what you saw today in the webinar, that the reported bandwidth will be horrendously low. I saw something like 10 gigabytes per second. Okay, this is absolutely intended and is part of the educational purpose of this example. And since it's so bad, it's kind of the motivation for next webinar's topic, where we show you how you can crank up memory bandwidth. The reason is that you're also measuring kind of the MPI, the PCI Express latency and the PCI Express bandwidth. So, you're not really measuring GPU bandwidth right now. So the low result that you may see is absolutely intended, and you'll be able to fix that after next webinar's topic. So this exercise will kind of come back in about 4 weeks. Christian, your Jacobi.
Yes. Okay. So Jacobi is closer to a real code than stream. Yeah. So it's a code that can profit from a GPU. So this is a simple solver of the Laplace equation in 2D. And that means you have 2 compute-intensive loops. The one loop performs the update of this array A, applying the stencil, and then the other loop copies A into a new, or whatever the name of the variable is called. That means that's what is used as a basis for the next iteration. So it applies this 5-point stencil, as illustrated here, over an array, and if the array is large enough, then you can actually see a pretty nice speed up on the GPU. However, we have to do a few things to get good performance. So task 0 would be to acquire reference measures on the host, in particular with multiple CPUs. And sorry, this should read without GPU. So there's an O missing. So first, measure the performance of the code on the host. This is what you want to beat sooner or later. Then you should go ahead and parallelize the most compute-intensive loop, which is the update of A. That means the application of the stencil. Again, do the right thing in order to get good performance on an NVIDIA or AMD GPU. I will provide reference values for NVIDIA, and maybe, Michael, you can add reference values for AMD GPUs as well. This is what we will present next in the next webinar. So really, the first step would be to get it up and running on the GPU. Then this will be about improving the performance. So first, you should go ahead and parallelize the second loop. And then we also have to improve the data management. However, we didn't hear the constructs, or we didn't see the constructs that are needed for the solution to actually in this webinar. So next time we will present the solution as a teaser for what's then coming in the webinar. And then task 3, you can actually do that already if you think about it. Optimize the scheduling of iterations for the GPU. This is about using the right clause at the corresponding construct to actually give the runtime more freedom to exploit the large degree of parallelism. Then, I can already add a teaser here. This will be about improving performance even further. So we can make use with this example of multiple GPUs. We can use the host and the GPU simultaneously. And this is then what we will discuss next time. I think that's it. Are there any questions at the moment? That seems to be not the case. So then thank you very much for your attention. I hope this was a useful webinar as an introduction to GPU programming. And as we have already announced a few times, next time, we expect you to have understood the basics that we presented today. And that means it will be about getting more performance of the GPU. So again, it will not be about completely new constructs, but it will be more or less about several clauses that optimize data movement, enable asynchronous kernel execution, and so forth. Anything to add, Michael or Franz?
No, just have to say, after four webinars, we finally made it on time.
We're getting better.
We're getting better.
Okay, thank you very much.
Thank you very much, Michael and Christian, for this great webinar. And everyone, see you at the next webinar. It's on Tuesday, 25 May, in a month. Thank you very much. Bye, everyone.
Folks, bye-bye.